Good morning. Today I'd like to talk about dot products of vectors. In particular, I want to think back to what motivated these things. So for the moment, we're back in the land of college algebra. So for now, we are ignoring our new and improved notation and doing things the old-fashioned way. If I have a point P in the plane, I'll think of its coordinates as being x1 and y1. Q will have coordinates x2 and y2. The distance across the bottom, x2 minus x1, will also be known as delta x, and y2 minus y1 will also be known as delta y. The Pythagorean theorem tells me the square of the distance that I'm after is just delta x squared plus delta y squared. On the other hand, if you let u be the vector that starts at P and ends at Q, that vector has components delta y and delta x for the first slot. U dot u, done the way that you do it back in Calculus 3, is delta x squared plus delta y squared. So if you want to do coordinate transformations that leave lengths invariant, it's going to be necessary that this dot product be invariant as well. I'm also going to revert momentarily to the matrix language we used before. Imagine that I replace columns in Rn with a matrix times that column, likewise for y. In matrix language, the dot product is x transpose y. I'd like to ask, if the dot product is preserved, what kind of thing does Q have to be? If I insist that the dot product remain unchanged, I can write the transpose of Qx as x transpose Q transpose. When I multiply that row by the column Qy, I have to insist that I get x transpose times y, which is the same as x transpose times the identity matrix times y. If I subtract this quantity from both sides, factor an x transpose off to the left and y off to the right, I find out that this quantity must be 0 for all column vectors x and y. In particular, if y is the same vector as x, then this would have to be true for all columns x. It's not difficult to see that Q transpose Q is symmetric. I is symmetric. X transpose a symmetric matrix times x being 0 for all column vectors x is enough, if you remember the linear algebra stuff, to conclude that the matrix in the middle must be 0. But if Q transpose Q minus identity is 0, that means that Q transpose Q must be the identity matrix. That means matrix Q has an inverse, namely Q transpose, and this is what we were calling an orthogonal matrix previously. We already knew that if a matrix was orthogonal, then it preserved the dot product. Now we know the reverse also. If one of these matrix transformations preserves the dot product, then it has to be one of those orthogonal matrices. At the moment, it's not clear why I've written this down, but I'm just going to say the usual dot product in Rn is you write one of the two vectors as a row, write the identity matrix in the middle, and write the other vector as a column and carry out the matrix multiplication. In Euclidean space, the square of the distance between 2 points was given by Pythagorean theorem if you're in 3 dimensions. Thinking of the vector that starts at one point and ends at the other, we also think of this as the dot product of the vector from one point to the other with itself. I'm going to go on and use the notation for vector components that we will use in our work here. Look at this, look at that, look at these two things again, and look at that again. To preserve as much of our ideas as we can, if I have 2 4 vectors, or in this particular instance just one, the u, I am going to define the dot product of u with itself to be this. I do the usual thing for the space components, but when I square the time component, I put a negative sign on it. Let's stop just for a minute and remember the significance of that. Why is there a negative sign there? Go back and look at where we were talking about the invariance of the space-time interval. And where did that come from? It came from the constant speed of light business. So ultimately, that negative sign there is because of the constant speed of light. Knowing what we know now, even though I'm thinking of this stuff as being as in Calc 3, I'm going to put quotation marks around those equal signs for reasons that should be obvious by now. These ideas led us to define the dot product to be this way. This dot product is invariant with respect to a certain type of linear transformation, an orthogonal transformation. By way of analogy, in special relativity using Minkowski coordinates, if I have the components of 2 vectors with respect to O, I'm going to define the dot product of the 2 vectors to be, if there were no time component, it would just be the usual Euclidean dot product. But in view of what happened in the space-time interval, for the initial term, I'm going to multiply u0 and v0 together and then put a negative sign on it. This will make this as to that as this is to that. So when we say dot product in special relativity, we mean this and not that. A reasonable question to ask ourselves is, there is a category of linear transformations under which this dot product is invariant, the orthogonal transformations. What linear transformations leave this dot product invariant? Another way to write the old dot product is to write calculus 3 style with indexes downstairs, components of u, the identity matrix, components of v as a column. You could also write that using the Einstein summation convention as Kronecker delta ik, and then we could use our upper index notation for vector components, ui vk. This is the sum over I of the sum over k of delta ik, u component I, v component k. The only time that you're going to get a non-zero term is when indexes I and k are the same. So this would be u1 v1 plus u2 v2 plus u3 v3. This is a different way of writing down the dot product. If you multiply it out, it turns out that the Minkowski dot product can be thought of this way. You write one of your vectors as a row, the other as a column. In the middle, you'll have a diagonal matrix somewhat reminiscent of the identity matrix, in that the x, y, and z slots have 1s in them, but the time slot has a -1. If you multiply this out, it comes up equal to the negative of u0 v0 plus u1 v1 plus u2 v2 plus u3 v3. This is the new dot product that we're talking about. The name of this matrix is the identity matrix, capital I. We usually denote its components by Kronecker delta. This is not the identity matrix, although it resembles it. We'll give this matrix a name. We call it eta. The Minkowski dot product can be written as eta alpha beta u alpha v beta, with the understanding that both alpha and beta are indexes of summation. Amongst the eta numbers, eta 0, 0 is -1, eta 1, 1, 2, 2, and 3, 3 are equal to 1, and all other eta values are 0. We have figured out that the old dot product is invariant with respect to linear transformations if and only if the transformation matrix Q obeys Q transpose I Q equal I, which we usually have written just as Q transpose Q equal I, but I want to write it this way for reasons that'll become clear in a moment. I want to figure out under what linear transformations is the space-time interval going to be invariant, or to be more precise about it, the dot product being invariant. To investigate this, firstly, suppose that the new Minkowski dot product is invariant with respect to some linear transformation whose matrix is given by lambda. That means if I were to calculate u dot v, namely that, and then I were to calculate the dot product of lambda u and lambda v, namely that, I would always get the same answer regardless of which columns u and v I'm talking about. Subtracting this quantity from both sides, I get that this must be 0. Matrix multiplication does obey a distributive law, so I don't feel bad about pulling the u transpose on this side out and the v on this one. Since this is true for all u and v, in particular it's true if the v and the u are the same quantity, it's not hard to see that the matrix in the middle is symmetric. The transpose of lambda transpose eta lambda minus lambda is the transpose of the first matrix minus the transpose of the second. Because of one of the linear algebra facts we know, though, the transpose of something times something times something else is the transpose of the something else times the transpose of the something times the transpose of lambda transpose, which would just be lambda. Eta is diagonal, so it is automatically symmetric. So it turns out that the transpose of the matrix lambda transpose eta lambda minus eta is lambda transpose eta lambda minus eta. The transpose of the matrix in the parentheses equals the matrix in the parentheses. The matrix in question is symmetric. This is relevant because we previously had a statement that said if vector transpose matrix same vector is 0 for all choices of u, then that automatically means the matrix in the middle is the 0 matrix. Lambda transpose eta lambda minus eta must be the 0 matrix. Lambda transpose eta lambda must equal eta. So let me summarize what we've figured out here. If the Minkowski dot product is left invariant by a linear transformation lambda, then that lambda must obey this equation. Lambda transpose eta lambda equals eta, where eta is the 4 by 4 diagonal matrix that looks just like the identity, except it has a -1 in row 0, column 0. What we just convinced ourselves of is if a linear transformation leaves the space-time interval invariant, then it must be true that lambda transpose eta lambda must equal eta. That doesn't rule out conceivably the possibility that there might be some matrices that obey that equation that don't leave the space-time interval invariant, but it's going to turn out that that's not true. If lambda is a matrix of constants, in the sense that they don't depend on the coordinates, that is, so that we have a linear transformation, and if lambda obeys lambda transpose eta lambda equals eta, then look at the dot product of the transformed vectors after doing the kind of algebra that we've talked about before. Here, lambda transpose eta lambda by hypotheses is eta. This quantity and that quantity are the same. So if I have a constant lambda with respect to the coordinates, so that I have a linear transformation, and if this is true, then the transformation lambda preserves the dot product. So to summarize, if I make a linear transformation represented in matrix form by replacing u with lambda times u and v by lambda times v, that transformation preserves the Minkowski dot product if and only if this equation is true. This gives us a way of identifying general Lorentz transformations. In ordinary Calc 3 parlance, written in matrix notation, the dot product U transpose V is invariant under a linear transformation if and only if the Q inverse is Q transpose. That is to say, Q times Q transpose is the identity, Q transpose Q is the identity. The linear algebra name that we gave that is, we say that the matrix Q is orthogonal. Written in a rather strange looking way, In this situation, the dot product is invariant when Q transpose identity matrix Q is identity matrix. For the Minkowski dot product, if I do a linear transformation, the dot product is invariant with respect to that transformation if and only if lambda transpose eta lambda is eta. Except for the name of the transformation, and except for the fact that the matrix in the middle and on this side is I here and is eta here, these two statements are very similar in spirit. Physicists give a special name for this kind of lambda. The fact that they call such a thing orthogonal is enough to drive a person half crazy. We should call this kind of behavior Minkowski orthogonal, or special relativity orthogonal, or some such name, but that's not what they do. That orthogonal and that orthogonal are not the same thing. So when we're speaking of this in the future, we're going to have to be very clear about which orthogonal it is that we're talking about. There is much more that could be said about these issues, and we may look into that at some point. But at the moment, I think we'll have enough ammunition here for a while to do a little bit of physics in this new setting. In the meantime, I hope that everybody has a good day, and I'll talk to you again soon.